Hi everyone, so my name is Tejas, and on behalf of my co-authors Amit, Siva, and Milan and Vinay, I'm pleased to present our paper Distributed Adaptive Speculative Decoding, Accelerative Large Language Model Inference with Context-Aware Draft Selection. This work addresses a critical bottleneck in deploying the large language models at the production scale. The sequential nature of this auto-regressive token generation. Before I dive into the technical content, I want to frame the scale of the problem. The system like GPT-4, Claude, and Llama 3 bus like the must generate the hundreds of tokens per responses. Each require a full forward pass through tens of billions of parameters that creates a real world latency that harms user experience. Our framework DST delivers 2.8 to 2.8 times speed up over standard auto-regressive decoding, a 15 to 20% improvement over fixed speculative decoding baselines, and 42% reduction in end-to-end latency in a multi-GPU setting, all with absolutely zero degradation in output quality. These numbers are verified across four benchmarks spanning code generation, factual QA, conversational tasks. We'll walk through the problem and our three core contributions, experiment results, key takeaways in approximately 20 minutes. I'll pause for the question. Let me set the stage by framing the core problem. The large language model generates output one token at a time. Each token requires a complete forward pass of the model for a model like Llama 3. B that means 8 billion floating point operating per token and typical response of 200 to like the 200 to 500 tokens requires sequential passes. Mm. There is no way to parallelize across tokens in standard auto-regressive decoding. This creates a fundamental bottleneck at Amazon scale where we serve millions of queries per day. Um, Speculative decoding offers an elegant solution to this bottleneck. The core idea is use small, fast draft model to speculatively generate multiple tokens ahead of the large language model. Then run the large language model once in the single parallel forward pass to verify all speculated tokens simultaneously. Accepted token reduce the number of sequential steps, yielding 2 to 3 times speed up without changing the output distribution. The critical insight is that verification is cheap. The target model can check key tokens in nearly the same time as checking one token because the competition is parallelizable across the positions. However, as we will see on the next slide, the existing speculative decoding system has significant limitations that prevent effective deployment in real production environment. So the prior work on speculative decoding, while promising, leaves three critical gaps addressed. First one is static drift model selection. Every existing speculative decoding system commits to a single fixed draft model for all incoming requests, but real LM needs about diverse workloads, code generation, factuals, and open-ended conversation summarizations. Second gap, single node execution constant. The entire body of speculative decoding literature assumes that execution on single GPU, but production LM service serving at Amazon, Google, or any other major companies provide a distributed inference across many GPUs and nodes. There is no mechanism in existing system to pipeline a draft generation and target verification across GPUs cluster. Critically, no fault tolerance for the hardware failure. The fixed speculation length key, every system we are aware of uses a constant key, typical 3 to 7 tokens, regardless of what it is actually happening at runtime. This is clearly suboptimal when the draft model is performing exceptionally well. DSD introduced three tightly integrated contributions that work synergistically. The context of a draft selection. Rather than committing to fixed draft model, we train a light neural outer just 0.13 million parameters that examines the incoming input and dynamically selects the best draft model from the router operates on embedding from the target model's first tier, adding the less than 1 millisecond of overhead per request. A single contribution improves acceptance rate by 15 to 20% compared to any fixed draft baseline. The second contribution, asynchronous distributed speculation protocol. We redesigned the speculation pipeline from ground up for multiple GPU execution. The draft generation and target verification are pipeline asynchronously across dedicated GPU workers. Coordinated by a CPU scheduler, we implement checkpoint rollback full tolerance so that GPU failure does not interrupt services. The system gracefully degrades back to the standard auto-regressive decoding if needed. In multi-GPU configuration, this reduces end-to-end latency by 40% Adaptive sched circulation and we maintain a sliding window of recent token acceptance statistics and continuously update K using an exponential moving average with hysteresis threshold. When the draft model is on or trick above 75% acceptance, increases up to 10. The key insight is these three components are not independent optimization. The router selects the best draft model, which maximizes the exception range that optimized key mechanism observes, which informs how aggressively the distributed pipeline should speculate. Let me now explain the routers in details. The router is two-layer MLP that maps input expression to a probability distribution over the draft model pool. Given the input embedding from the first layer of target model, it computes the probability vector over the available draft models and select one the highest probability. So this is the right router architecture. And then on the right hand side, it's a task-specific draft performance for code generation, factual QA, summarization, conversation, and creative writing. Um, the distributed protocol is an engineering heart of DSD. We partition the GPU cluster into three function roles: draft workers, CPU coordinators, and target workers. And at the end, we see the three key optimization. The first one is checkpoint rollback. On a GPU failure, the coordinator rolls back to ST-1 and we assign to backup resumes with this formula. Token streaming, and the draft worker streams tokens incrementally and use the first token latency by 40%, waiting for the full case sequence. The third one is FP16 compressions. Now, the third contribution is the adaptive speculating length mechanism, and I think one of the most practical important innovation in DSD. The intuition is simple, but the impact is significant. Consider two extremes. If your draft model is generating tokens that the target model accepts 90% of the time. So on the right hand side, there is a speed up versus speculation length for fixed K versus adaptive K DSD that how algorithm is. Now, this is our setup. This is the hardware requirements. This is the model that we use during the experiment, and this is the benchmarks that we have compared against. And this is our baseline that we have set for our experiment. Um, Now, these are the results. Let me walk you through the main result carefully because I want to highlight what is and is not surprising. Headline number DSD achieves 39.2 tokens per second on empty bench, 2.42 times speed up on human eval coordination. It reaches 43.1 per second and 2.60 times per speed up and on MMLU, 41.8 tokens per second for 2.58 times speed up across all benchmarks. DSD outperforms every baseline, including the best speculative decoding method um, by by 10 to 24%. Importantly, look at the quality perplexity differences exactly 0.0. Belu scores match precisely at past one code correctness is identical to the order baseline. So these are all the numbers you got: speed over AR, best fixed baseline, perplexity data, and code acceptance rate. Um, so I think let me now discuss DSD works best where its current limitations lie, where we see the most promising future direction. DSD delivers the largest gains in three scenario. First, task diverse production workloads, queries, mixed code generation, factual QA, conversation exchanges, batch inference, latency critical interactive system, multi-tenant cloud with 28% latency reduction. But there comes with limitation. The draft pool curation currently requires manual selection of diverse set of draft models. This is manageable in practice. We choose our four models based on known specialization, but automating this selection is an open research problem. The router also requires a cold start training, um, and which may be a burden for niche domains. Transfer learning from adjacent domains can mitigate this. Finally, for very large target models such as 70 million parameter models, keeping multiple draft models in the memory simultaneously becomes challenging. Or lazy loading mechanism partially addresses, but a memory constraint remains a practical consideration. Three future direction excites us most. The first is co-training draft and target models and end-to-end could push the acceptance rate well beyond our current 72 to 76% ceiling. Second, extending the framework to speculative batching, handling multiple concurrent requests with different draft models. and present interesting scheduling challenges. Third is federated draft running in multi-tenant cloud deployment could enable the personalization draft model tuned into the individual users' interaction patterns. So let's put on the conclusion. So the conclusion is let me close this with a brief summary and then key take-home messages. TSD propose a comprehensive um, framework for accelerating the LLM inference through the three synergistic innovation. Context-aware routing dynamically matches each input to its optimal draft model and delivering 15 to 20% high token acceptance compared to any fixed draft. An asynchronous distributed protocol enables the fault-tolerant multi-GPU execution with near linear scaling efficiency and 42% end-to-end latency reduction. Adaptive select speculation length continuously optimize key based on real-time acceptance statistic, preventing both under speculation and mistrust. Together, this contribution achieved 2.6 to 2.8 times speed over standard auto-regressive decoding. Our strongest result is 2.66 times on code generation, while getting exactly the same output quality as a baseline at 4 GPUs and throughout the reaches 142.8 tokens per second with 90% scaling efficiency. I want to emphasize the practical significance of this role. At 2.7 times speedup translates to a truly 61% reduction in PRs per query. And the production scale, this is a massive cost reduction and enables the deployment of larger, high quality models within the same infrastructure budget. Our implementation and the benchmarks are available on the request. We hope DST provides a productive foundation for efficient LM serving in the production distributed system. Thank you. Um, I'm happy to take any questions as this is recorded video. I would like some questions. Uh, anyone wants to ask any questions? I'm the primary author on this paper, so you can ask me any question. My name Tejas Praveen Bhai Patel, and and this is my email ID. You can ask me any questions here, and I'm like handing this presentation as a primary author. My name is Tejas Praveen Bhai Patel, and thank you for giving me an opportunity to present here, and thank you so much.